we're going to do a video going over buffers and just also some general acid-base things and figuring out what is a buffer, what makes a good buffer, choosing buffer components, what's buffer capacity, and also just finding pH and which equations to use when and recognizing when you have a buffer or not. So a buffer is something that resists change in pH, and a buffer is a solution containing both a weak acid and its conjugate base. And so the way that it works is the weak acid component of your buffer will neutralize any hydroxide added. So if you add a strong base to your solution, the weak acid will consume it, will use it up. And the weak base component of your buffer will neutralize any hydrogen ions being added. So to a buffer you could add some base or some acid, and the pH won't change very much. And here is a kind of pictorial picture of it. If you've got a buffer with equal concentrations of its weak acid and its conjugate base, if you add some strong acid to it, you'll notice that some of the weak base will be converted into the conjugate acid. If you add some hydroxide ions to it, some of the weak acid will be converted into the conjugate base. And this will result in not a very big change in your pH. And if you look at this equation for finding out the pH of a buffered solution, it's pH equals pKa log A over HA. And so since this is logarithmic, in order for the pH to change by a factor of 1, this ratio would have to change by tenfold, right? You'd have to all of a sudden have 10 times more one of the components. So that's why changing the concentration of these by small amounts, which is happening here, isn't going to change the pH by very much. Here's a picture of it. Again, you can kind of see the actual components of a buffer mixture. So your buffer has some of the weak acid and its conjugate base. If you add a strong acid to it, you notice that, like in this original picture, I had 3 of my weak acids, 3 conjugate bases. If you add some strong acid to it, I've got 5 weak acids now and 1 of the conjugate base left over. If I add some hydroxide, now I've got only 1 of my weak acids left and 5 conjugate bases. In both these cases, though, the log of the ratio is not going to change by very much, so the pH is going to stay relatively constant, and that's how your buffer works. So here is this equation you can use to find the pH of a buffer. This is something that I'm seeing tends to get overused, so make sure you are only using this equation when you have a buffer. And you have a buffer if you have some of the conjugate acid and the conjugate base. You have to have both the weak acid and the weak base in that conjugate acid-base pair. If you have a solution of pure weak acid, you should not be using this equation. If you have a solution of pure base, you should not be using it. You should only be using it in situations where you have both the weak acid and conjugate base pair. The pKa is the negative log of the Ka value, and this is the concentration of the conjugate base and the weak acid. Notice that when the concentrations of these are equal, when HA equals A minus, so when your weak acid concentration equals your conjugate base concentration, this value becomes 1, and the log of 1 is 0. So when the weak acid and conjugate base concentrations are equal, then pH equals pKa. And again, it's only true when you have equal amounts of weak acid and conjugate base. This is another fact I'm seeing overused in some cases. So another way of looking at it, rather than using this equation right here, is you can also use your Ka expression, right? Ka equals H times A over HA. You can rearrange it to solve for H plus, and notice that when you do that, you will see again that when HA and A minus are equal, that your H plus concentration is equal to your Ka value, and that means your pH is equal to your pKa. And the other thing you'll notice is that if your buffer, if these concentrations are not equal, let's say you have a little bit more HA than A minus, this ratio will be a little bit greater than 1, meaning your H plus concentration will be a little bit higher. So that'll give you a pH that is a little lower than your pKa. Let's say your buffer has a little bit more A minus than HA in it, then that means your H plus concentration will be a little bit less than your Ka value, and your pH will be a little bit greater than your pKa. And that makes sense because, if you're adding a little bit more acid, you expect your pH to drop a little bit. If you're adding a little bit more of the base component, you expect your pH of your buffer to go up by a little bit. So that's just something to keep in mind. So a couple different ways of making a buffer. What many of you did in the lab we did is we took a solution of weak acid and the salt of its conjugate base. So for example, you might have aqueous hydrofluoric acid and add some solid sodium fluoride to it. So HF is your weak acid. The fluoride ion, once this dissolves, is going to be your conjugate base. You could take a solution of weak base and the salt of its conjugate acid. Some of you did this. So ammonia is a weak base. The ammonium ion is its conjugate acid. So you might take a solution of NH3 and add some solid ammonium chloride to it. Or you could also do a titration and stop before you reach equivalence. So what happens during titration, let's say you start with a weak acid and you're adding a strong base to it. During that process, some of your weak acid will turn into the conjugate base. And if you stop before equivalence, and equivalence is when all of this will have reacted. So if you stop some point before that, you're still going to have some excess HA, and you will have made some A-. So you're going to have both the weak acid and its conjugate base present, so you will have a buffer. Buffer capacity is the ability of a buffering solution to accept the addition of hydrogen or hydroxide ions before its pH starts to change significantly. So if you have higher concentrations of your weak acid conjugate base, you're going to have higher buffer capacity. So to make an effective buffer, there's two things you want to think about. The desired pH range, so the pKa of your weak acid component of your buffer should be similar to the pH you're aiming for, and the buffer capacity. So the more concentrated your buffer components are, the greater your buffer capacity will be. So a solution with 1 molar weak acid and conjugate base will have a greater buffer capacity than something with 0.1 molar weak acid conjugate base. So some scenarios, and with these ones I'm going to give you a scenario and you might want to pause the video and stop and try the problem, then you can check your answer. So I want you to think about how are you going to find the pH of the solution and is it a buffer? So some of these will be buffers and some won't, and I want you to practice distinguishing between them. So here's an example. You've got a 1 molar solution of hypochlorous acid, and I'll give you the Ka value. So the question is, how are you going to find the pH, and is it a buffer? So you can stop and try that. The answer is, since this is simply a solution of a weak acid, you should be setting up an ice chart, and you're going to write out the Ka expression, and you're going to solve for the pH that way. So you're going to say, okay, what happens when weak acid is in water? It's going to dissociate a little bit, so you're going to write out that equilibrium reaction that occurs. In your ice chart, I'm starting out with 1 molar acid, I'm starting out with 0 of these. This is going to go down by some value x, up by some value x. If I plug it into my Ka expression, I end up with x squared over 1 equals my Ka value. If I solve for x, notice x is giving me the H plus concentration. So to find the pH, I need to take the negative log of the H plus concentration. So I'm taking the negative log of my x value, and I should be getting 3.73. So this is a solution of weak acid. It's not a buffer. It's got a pH of 3.7. Here's another scenario. Let's say you took 1 mole of hypochlorous acid and combined it with 0.4 moles of sodium hydroxide, and that was all dissolved in 1 liter. So the question is that a buffer? How do you find the pH of that solution? So what you want to spot is that you have a weak acid and you're adding a strong base to it, but you're adding less strong base than you have weak acid. So it's like you're doing a titration, but you're not quite at equivalence yet. So that means you are in the buffer zone. So yes, this is a buffer, and we will show why. So here is the titration reaction that happens. So you've got 1 mole of your weak acid. You're adding 0.4 moles of hydroxide to it. And what I'm doing up here is just some stoichiometry. So I'm saying, how many moles do I have? After it all reacts, what's left over? So they react in a 1-to-1 ratio. So all of my hydroxides can get used up. 0.4 of my acid will get used up. That'll leave 0.6 moles of acid behind. And in that process, I'm making 0.4 moles of my conjugate base. So notice now I have a buffer. I've got some of my weak acid and my conjugate base present. And again, this is really similar to a calculation you do in a titration. So after I figure that out, I'm going to go down and make an ice chart. And in my ice chart, I should plug in my molarity values. And since they're dissolved in 1 liter, that makes finding my molarity really easy. So I plug it into my ice chart, and notice that when I have a buffer, what's different about the ice chart is I'm going to have a value on both sides of the arrow. So I'm going to start out with some of my reactant and some of my product. So I plug this in my K expression. Rather than having x squared, I will see something like this. X times 0.4 divided by 0.6. equals 3.5 times 10 to the negative 8th. So when I plug this in, solve for my H plus concentration, find the pH, you'll notice it's 7.27, which here the pH is pretty similar to my pKa because again I have a buffer. Notice when I had just the pure weak acid, my pH is not close to pKa. So pH is only close to pKa when you have a buffer, when you have, relatively significant amounts of both the weak acid and its conjugate base. So here's our problem here. Again, it's basically a titration problem. You have a buffer because you're before equivalence. You've got both weak acid and conjugate base. You can also use the equation pH equals pKa plus log A over HA to solve this problem. So you can try that. You should still get 7.27 as your answer. All right, another scenario. Let's say you've got 1 mole of hypochlorous acid and 1 mole of sodium hydroxide. So take a moment to try that. Ask yourself, what's the pH? Is it a buffer? In this case, you'll find that you have added equal amounts of moles of a weak acid and a strong base. So this is like you're at the equivalence point of a titration. So what happens here is all of your weak acid will react with your strong base, and you will have 1 mole of conjugate base left over in your solution. So what you have now is you have a solution of the conjugate base. So no, this is not a buffer, because all I have now at this point is the conjugate base present. There is no weak acid component to this solution, so it's not a very good buffer. I can find the pH of it though, and the way that I do that is by looking at the Kb expression. So I'd say this weak base is going to react with water. Bases are hydrogen takers, so it will create hydroxide ions and HOCl. And I can write an equilibrium expression for this. We leave out water because water is a pure liquid. And the value that I should use for this equilibrium expression is Kb. And we aren't given a Kb value, we're given a Ka value. But we know that for a weak acid and its conjugate base, Ka times Kb equals Kw. And Kw is 1 times 10 to the negative 14th. So we can use that to figure out what the Kb value is for the hypochlorite ion, that's the ClO minus. And we can plug that into our expression and end up with x squared divided by 1 equals this Kb value, and you will find that your pH equals 10.72. Okay? Another scenario, let's say we have 1 mole of HOCl with 1 mole of NaOCl. Is this a good buffer? What's the pH? If you're looking at what we have here, I have a weak acid and I have a salt containing its conjugate base. So this is a good buffer because we've got equal amounts of weak acid and the conjugate base, which is the OCl minus ion. And since they are present in equal amounts, we have 1 mole of each, then pH is going to equal pKa. So finding the pH here is relatively straightforward. We just take the negative log of the Ka value, and you'll find that the pH is 7.46. And again, this is only true because we have equal amounts of weak acid and its conjugate base present in your solution. So last scenario, let's say you have 1 mole of HOCl combined with 1 mole of HCl. Would that be a good buffer? What's the pH? So this scenario, you want to notice that you are adding a weak acid and a strong acid. So you've got 2 acids, no base components. This is not a very good buffer. You can figure out the pH though by looking at, your pH is going to be mainly determined by your HCl concentration because that's your strong acid. So when you stick 1 mole of HCl into 1 liter of solution, it's going to completely dissociate and create 1 mole of H plus ions. So your pH is going to be mainly determined by your strong acid component. And if I try to figure out what that was, if I've got 1 mole of HCl dissolved in 1 liter of solution, that means I have 1 molar H plus ions. And so if I take the negative log of that, I'll find my pH is 0. So yes, you can have a negative pH and a pH of 0. So it can go below 1. So there you go. And last scenarios to look at, is it a buffer? So here's 4 scenarios to look at. You can pause, ask yourself, is this a buffer? So first scenario, no, it's not a buffer because HCl is a strong acid and this is the salt of a strong acid. We want them both to be weak. This one is not a buffer because we have a strong acid and a strong base. So when I put those together, I'll just end up with salt water, not a good buffer. This case, yes, it is a good buffer because I've got a weak acid in HCN, and I've got the conjugate base in the CN minus ion. And this is also a good buffer. I've got the bicarbonate ion and the carbonate ion. And so that is a weak acid conjugate base pair. The way that you would spot these, what you'll notice is the only difference in these two formulas is that the weak acid has one more hydrogen than the conjugate base does. So that's what you're looking for there. They want to be separated by just one hydrogen. So that's some practice with buffers and pH and general overview.